So there are two things which I wanted to mention. My name is Govindarajan. I was retired faculty from Institute of Mathematical Sciences. And Tamil Nadu Science Forum was started around 1980 when I was a graduate student. Unfortunately, I was also one of the people who founded this place, this program, which has been successful for the past some 50 years now. But we have grown into several areas after that. We even want to do the programs at the school level, primary school level, rural areas, etc. So there are several activities associated with the Tamil Nadu Science Forum. The popular science lectures is one such activity where we have one on health, we have one on women's education, we have a literacy program in which many of us are involved. We also run a very nice children's science magazine in Tamil called Tulil, and it is meant for, please, you can join. It's meant for students below 8th standard or 6th to 8th standard, less than that, around that, who can read. That is the only thing. So we also have an English version thing called Jantar Mantar, which is also available. And joining Science Forum is not a big thing. You have to only tell some of the activists here who will enroll you. The important thing is joining is not difficult, it's not very expensive. But one thing is, important thing is, what is it you can do to contribute? Many of the people who join like that from colleges and schools, they are in touch with us so that they ask programs to be conducted in those places. So Christian College is one, Loyola College is one, Vivekananda, or many other places now. They want some programs to be conducted, and we try to provide some kind of support system so that it can be done. So this is as far as the Science Forum is concerned. I didn't want to take too much time. Now we have every year we have been conducting programs on in October after the Nobel Prizes are announced. And this year also the 3 lectures, one was conducted last week, and this is the second one, which was on physics, and the third one will be next week on Saturday in the same library here. The hall will be decided, but it will be here, and on chemistry. So this is the thing. So today's program is about physics, the great achievements which were there, and every year it has been fairly successful. A lot of people showed interest in knowing about why is it they gave the prize. That is the question. In order to create this enthusiasm, we even conducted from last year, but this year is little more, a kind of a competition 1 month before we announced to various colleges and students in our list of emails which are there. And we conducted a competition, predict who will get the prize. So obviously now the facilities of ChatGPT and the thing, we don't care. You use whatever you like, and you can provide only one form in which you can predict what you want to say about the prices. But if you want to predict many, you are welcome to do, but the latest one will be taken. The rest will be discarded. Okay. So this was what was done. And unlike last year, this time it was fairly successful. And to our surprise, in chemistry, some 12 people, 12, I don't want to call students, 12 participants have predicted more or less accurately. They predicted 2 other names and area, etc. Some predicted 1 name and the area, kind of thing. And we, as promised, we are going to give prizes next week. And physics also, a couple of people have predicted. And to some extent, we are happy about this kind of a participation. So what we want to do is, okay, you go and consult. You consult any faculty member, you consult any professor, because after all, they are not astrologers, right? They will have several names. But at the end of the day, you would be asked to find out the person, candidate among the areas. And your only one of your thing will be taken. So you at least it will force the students and participants to go through some of the work more than simply the thing, and what they expect. They can apply any probability theory for predicting this. And surprisingly, we are happy that the number is increasing. We want to increase it to some good number of predictions next year. Okay, so this year it will be done next week in the library itself, the prize distribution and chemistry Nobel Prize. Discussion on that will be done. Today, we are having the physics one. Physics one is also my favorite. It's also my subject. And this is, we have been always teaching, can you just, if all this room is locked, can you go out of the room without breaking any of the walls? The physics tells you, yes, it is possible, but the probability for that is extremely low. And we do find in radioactivity, alpha particles come out of the nucleus just even though they don't have sufficient energy. It is like you are inside a room locked, and the energy required, you don't have that kind of energy to cross the barrier. You cross the barrier. It is almost like you have to cross Everest without climbing up, but go through a tunnel through it. We call it quantum tunneling. And that was a kind of a prediction, which was fancy thing, which was done in several decades back, which was people were aware of it. But alpha decay is one of the major things in such a thing, which was successfully explained using that. Alpha decay does happen, and we know people, it doesn't have enough energy to cross the thing. The only way in which it could have crossed is by quantum tunneling. That is the way it was explained. Now there is this new kind of experiments. Actually, people see where you cannot be there and you are there. Okay, you are not there. It is not possible. But you cross a barrier where you are not allowed to go there and stay there, because it is impossible. So such things do happen, and I don't want to take too much time. I just want to introduce the speaker. Dr. Siddharth Dhomkar is a physicist. He is from IIT Madras. In fact, I've been chatting with him for the past 15 minutes. So this is a complex world around quantum theory and many other areas. He completed his undergraduate and master's studies in physics at the University of Pune. It so happens wherever you have been there, I have some friends. Okay, so this is one more thing. And after which he pursued his passion for teaching as high school teacher. That's amazing for me. Later earned his PhD from the City College, New York.
Yeah, City University and then City College.
Yes, I know one more person there, Parameswaran Nair.
Yes, I know.
Okay, one more. In fact, so this is the thing where he investigated magneto-optical effects in quantum structures and their potential use in devices such as solar position at the solar cells and lasers. Postdoctoral position at City College, New York. Just now he mentioned, and various activities. The list we have actually sent along with your emails. Okay, so I don't want to take too much time because already we are 20 minutes late. Usually we start around 11:05, 11:10 maximum, and we don't want to delay because of lack of audience. Whoever 10 people are interested is good enough for us. So it's usually our physics programs are very well attended. And now I will ask Dr. Siddharth Dhomkar to start his explanation for why the Nobel Prize this year was for this work in 2025. For these people, John Clark, John Martinez, for the discovery of macroscopic quantum mechanical tunneling and energy quantization in an electric circuit. And his pictures are very interesting. Cat is out. The circuits are quantum. The world is quantum. You can't escape it. There is nothing like classical. Classical is only approximations. Okay, the world is quantum. Now it's up to you, Siddharth.
Thank you, Professor. I don't think I need mic for this audience. Can everyone hear me?
What about at the back?
At the back?
Yeah.
Okay.
At any time,
I teach without mic. because otherwise people, the ears will blow up. Okay. So, okay. So thank you very much. I'm delighted to be here, especially uh, I love sharing science with people, whoever is interested. Okay. So do bug me, meaning I'm going to talk about something that even I'm confused about. Okay. So if you are confused about it, don't feel shy. Okay. So the way I'm going to do this, we need to actually, we need to learn a lot in 1 hour. Okay. First of all, we need to understand what is quantum. Why do we need quantum? We have Newton. We have F equal to ma. We have this ball, right? I throw this ball up. I know how to calculate the trajectory. Newton has shown everything. Why do we need even quantum? First thing, we need to learn that. Okay. Then professor mentioned that tells us something incredible can happen. This ball, if I throw, even with less energy, can pass through that wall. That's the crazy thing that quantum teaches us. But why do we even care about it? I'll tell you about the story about this simple looking photograph. If you are a good experimental physicist, you will look at this photograph and something incredible will come out of it. Okay, so I'll talk about that. Then we need to talk about superconductivity, which is at the heart of this year's Nobel Prize. Okay, superconductivity. We all know conductors, copper, aluminum. We want to understand superconductivity. So that's the second part. And the third part is actually what these people did. 2 Johns and 1 Michael. These 3 people got Nobel Prize this year for doing something, okay, that is related, that combines superconductivity and quantum tunneling so that you see these phenomena in a device that is millimeter sized. Millimeter is bigger than your hair, right? Millimeter, all of us can see. So all of these things are happening at a millimeter scale now. Okay. And that's what we are going to learn, hopefully. So the idea is this. This is the biggest section. After this section, I'll take a break. If you guys have any questions, let me know. Okay. Because I don't want to move forward without you understanding the first part. Okay. So after this, I'll take a break. If you have any doubts, we'll catch up. Okay. So let me start. Yes, 1 hour total, right? Okay. So in order to start with quantum, I need to take you to 1900s. Okay, end of 1900s. What had happened in 1900? 1900s is an era where physicists thought they have explained everything. Faraday, Maxwell came up with electricity, magnetism. They showed that electricity and magnetism, they are related, right? So you have electrons moving around generating currents, but if they move, you also get magnetic fields. Everything is connected. That's Maxwell and Faraday. By 1880s, in a way, things were very clear as far as electricity, magnetism is concerned. Then there was thermodynamics. The steam engines were getting better and better every day, right? And thermodynamics is not simple. You see, we have lots and lots of atoms. Obviously, people did not know exactly that there were atoms, but they kind of had envisioned that there must be some small unit, right? And you don't know position and velocity of each of these atoms. Even in the room at the moment, you don't know where the molecules are. But you can still predict, if I turn on the AC, how long it would take the air on the other side to cool. That's how we design the ventilations in our rooms, right? We know what power of AC we need to use in order to cool a certain area. But if you really want to use Newtonian mechanics and look at each and every molecule, calculate its kinetic energy, and then decide what AC power you need to use, that would be impossible, right? But we still did it, meaning with heat engines. What are heat engines? This is what it is. So it was some kind of an emergent theory, which is kind of, if you bring things together, multiple particles together, they have different properties, like wetness of water. Okay, wetness of water is a property when only multiple H2O molecules come together. There is no wetness for a single H2O. You bring particles together, they interact and they create something new because of the interaction. And that's what happens with temperature. There is no temperature of a single molecule. But then there is a temperature of a gas. Why? Because temperature is basically the kinetic energy, how fast they are vibrating. Okay. So anyway, so all of these statistical phenomena were being discovered at the end of 19th century. And then just to tell you how people were feeling, most probably this is not his quote. Okay. This is not what Lord Kelvin said really. Lord Kelvin was the president of Royal Society, 1895, I think. And this is associated with him. Maybe he said something similar. What did he say? There is nothing new to be discovered in physics now. All that remains is more and more precise measurement. And this person had calculated age of the sun. It was 5,000 years according to him. And he did not like it because Darwin just came before, 10 years before him, said we need at least million years to actually show that the evolution works, right? You start from a single cell, you get human beings. You need at least million years, okay? So sun cannot be 5,000 years old. So people were missing lots of information, but people say ignorance is bliss, right? If you don't know what you don't know, then you always think that you know everything. That's what's happening, right? So that's what he said. But obviously, universe is much more miraculous than you think it is, right? So then people started doing some experiments in 1890s, okay? And I'm going to talk about some experiments from 1890s to 1910, okay? 1920 maybe, okay? 20, 30 years that completely changed how we look at the world, completely, okay? We had no other way to actually make this jump, okay? So first experiment, okay, I might jump around. This is not exactly how it happened, but that's the beauty of giving a lecture in 2025, okay? So now I can put everything together, okay? So first thing, black body radiation. As far as physics is concerned, we are all black, okay? Whatever has any temperature, okay, temperature different from the surrounding is a black body. It's going to radiate. That's what we call thermal equilibrium, right? You have a hot object, you keep it in the room, it will radiate heat, okay? Now what you can do actually, you can actually look at it and plot in which wavelength the heat is getting radiated, the energy is getting radiated, okay? If you do that, then if you plot it for a sun, then it looks like this. That's why we use silicon solar cells. You need to, or that's why the way photosynthesis works, the wavelength it absorbs is related to sun. What wavelength sun is emitting? Sun is at a particular temperature, it will emit a particular wavelength. Okay, this is the curve. Okay, so it's an electromagnetic radiation. Light is an electromagnetic radiation wave and is getting radiated. Okay, you can look at red hot iron. Why does it look red hot? Because of its temperature. And it's not only iron. You heat any object at that temperature, it will have a certain glow. And the color of that glow actually tells you what's the temperature of that object. If you look at me, okay, I'm too excited right now. So most probably my temperature is fairly high. If you have an infrared camera, then you will see something like this. So even I'm glowing, okay? So everyone glows. You keep doing this and then you can do this for lots of objects. People did these very precise measurements and what did people see? You can plot. Now you can use known Newtonian mechanics and all, and the curve that you get, okay, I don't want to go into the actual physics of it, but the curve that you would get would go something like this. There is no coming down. If you use Newtonian mechanics, whatever laws were known, what you would get, and the reason is because this is high energy side, this is low energy side. Okay, high energy side, there is no bound as far as Newtonian mechanics is concerned. There is no any object can emit anything. It's all continuous. Meaning this ball I can throw with whatever energy. Newtonian mechanics wise, I can throw it with whatever energy. There is no bound at all. Okay, so people were unable to explain this. And then this was a problem, nagging problem for 10, 12 years. A person called Max Planck in 1900 said, okay, this is a trick that many students play in the exam. What's the trick? you look at the final answer, you know the final answer. Okay, you already know the final answer, and somehow you do something to the answer so that you get the final answer. Okay, that's exactly what he did. What he did, he looked at the plot, he said, what do I need to do to get this plot? He said, what I need to do is I need to say that energy, when it's getting emitted, it's you cannot emit any energy. Okay, it's getting emitted in certain packets. Okay, certain packets, and the size of that packet depends on the wavelength of the packet. Okay, so larger the wavelength, lower the energy, or larger the frequency, higher the energy. Wavelength and frequency are related, right? So larger the frequency, higher the energy of the packet, and then you can only have energy emitted like this. You can have molecules vibrating. How are we generating the heat? Molecules are vibrating in all possible ways, but then they cannot vibrate with whatever energy. They will have to vibrate with certain energy. Okay, just assume this. Okay, he says just assume this and see what we get. He was able to get the curve. Okay, so what he's saying is that only certain energies are allowed. Only certain. That's what we mean by quantum, quanta of energy. Okay, a box. So I cannot give you whatever. Okay, quanta of energy. That is one thing. But he himself did not believe in it. He said, oh, it's some mathematical trick. Okay, there is no underlying physics. Don't believe in my results. This is I'm doing some mathematical trick to get this result. Maybe there is something different happening in reality, but this is how I am explaining it. Okay. Then what happened? Some other experiment, photoelectric effect. Yeah, what is it? You have two metals. Okay. You connect them, and then there is an evacuated quartz tube, meaning it's just vacuum inside. Okay. And then you shine light, and you shine light with different wavelength. Okay. Here it's a red wavelength. Now, what people were seeing is that when you shine light with blue, some of the electrons, I mean, in some metals, the electrons were getting emitted and you get the current. So electrons are actually coming out of the metal when you shine light. But the crazy thing was that it was not the intensity that was giving you more electrons. I mean, it was giving you more electrons, but there was a threshold, meaning let's consider an example. Let's say I have aluminum. I shine light. I shine red light, nothing happens. Even if I increase the intensity of red light, nothing happens, which is kind of counterintuitive, because what you would think is that the intensity is related to energy. Like if I give more intensity, more things should happen, but nothing happens. But then if I go from green to, let's say, blue, then suddenly electrons would pop up even at lower intensity. So again, this was showing something that Planck said. Okay. What is this? This means that energy is related to actually wavelength. What is the red, green, blue? These are wavelengths, different wavelengths. Blue has more energy, red has less energy. That's what it is. So Einstein saw this, okay? And in 1905, this is brilliant, okay? Einstein actually just looked at experiments from last 20 years, and they were from three different fields. One, Brownian motion, one, spatial theory of relativity, and third, photoelectric effect. And this is why he, by the way, for photoelectric effect, he got the Nobel Prize. Not for spatial theory or anything else, not for general theory. He got Nobel Prize for photoelectric effect. So he looked at the data from last 20 years and said, you see guys, we have to take this seriously. We have to take Planck seriously. We have to take all these experiments that were happening with the interferometry and all. I don't want to go into spatial theory, but whatever. So he said we have to take it seriously, and we have to really say that these waves have quantized energy. So in a way, these waves are made out of small boxes in a way. Okay, you can club them together, but it's a counterintuitive thing. Wave, how can it be made out of particles? Okay, but now what has happened? Planck said that there are certain energy levels. Now Einstein said that yes, you are right. These this light is made out of these small photons. Okay, that way you can explain it now. Okay, because even if you shine lots and lots of photons with lower energy, you cannot remove some electrons because they are tightly bound. Once you give enough energy to those electrons, they are going to jump out. So only when you change the wavelength of light, you can do this. Okay, so that's what he said. So what have we learned? Light is a wave and a particle at the same time, and then it has, these particles have discrete energies. Okay, good. Third, atomic spectra. We can do this experiment. These look like actually fairly new lights. You should do this experiment in your college or school or wherever you can. Yes, if you have a prism, actually you can. What do you expect? If I put a prism in front of this light, what do you expect? Multiple colors. How many colors you think? You will get a continuum? Why? Okay, so it depends on how good your infrastructure is in your whatever. Like, I think this is a fairly good infrastructure. So in the recent year, all these lights are made out of LEDs. Okay, so in principle, they only have red and green and blue LEDs inside. Only 3 colors. So if you see, you will get actually 3 peaks. Okay, not a continuous band. The older tube lights, you will get like a continuous spectrum. Why does it look white then? Because the sensors in our eyes, they are only of 3 type, red, green and blue. Okay, so we see it as a white light. Anyhow, you do this experiment with helium, hydrogen, okay, and then what you get is very sharp lines. Okay, now why sharp lines again? Okay, these are very sharp lines. So then Niels Bohr came and he said, you see guys, photons, the light is already made out of these packets, photons. Maybe everything is made out of packets and everything is wave simultaneously. Okay, sounds weird, but this is what he said. He said that there is this nucleus, the electron is orbiting around it, and then only certain orbits are allowed. Only certain orbits are allowed. He also received a Nobel Prize. Okay, this is, we are in around 1910, 1913. That's when this was happening. Okay, slowly moving forward. 1905 is when Einstein predicted this photoelectric effect and other things. So now he's saying that similar things, whatever is happening with photons, which is light related particle, or right, is also happening with matter, electrons. Electrons also actually have certain orbits. Not all orbits are allowed. Like this ball, I can throw it with whatever energy I like. But it seems like here electron can only have certain discrete orbits. Okay. Then now I'm going to actually go back to 1895 because I like this experiment. I'm an experimentalist, so what I feel is like, if you the good what do you call, the skill of an experimentalist is that you do not you should not put anything under the rug. You should not say, oh, that just happened for some reason, I don't know. Maybe that's the key thing. Okay, that's the key thing. That's what you need to. So you have to always observe and ask questions. So Henry Becquerel, 1895, he was doing some experiments with photographic plates. Most probably you don't even know what photographic plates are. You are all using digital cameras these days. Photographic plates is basically wherever you shine light, it's going to get exposed. Okay, and then that's how people used to get the photographs 20, 30 years ago, until 20, 30 years ago, right? So this is the technology that he was working with, and somehow in his lab there was some radioactive material as well lying around. So one day, at least this is the story, okay? The story is that one day he was in rush, he had a beaker with radioactive material, he put that on a photographic plate, put it into a drawer, he went home, came the other day, looked at the photographic plate, it was exposed. He was working in a dark room. How did it get exposed? Okay, so a person, a usual person would have just thrown that photographic plate, would have gone on to do whatever he or she was trying to do. But he was very curious. So he said, why did this happen? So what did he do? He put a coin in between the beaker and the photographic plate and did the same experiment. Okay, very simple thing. And he saw that wherever there was no coin, he was getting this glow. This is the picture from his paper, 1895 paper. Okay, so research paper. So what was happening? Some very energetic radiation was coming out of these atoms. Okay, now this is kind of crazy. If they have enough energy, then why are they sitting there in the first place? You agree? If you have enough energy, then why would you sit there? If you don't have enough energy, then why would you come out? So it's kind of crazy, right? I mean, they're coming out probabilistically, and it feels like a wave. It's like a radiation that is coming out. So some wavy thing. Obviously, later on, Marie Curie went on to do fascinating work on radioactivity. She won 2 Nobel Prizes. Actually, that's what killed her. She did not know that. Okay, back then, she did not know that. Even if you go to her office, her knob still is more radioactive than the background at the moment, because she was working with radioactive substances all the time. Okay, and this is not a chat GPT generated picture. This is a real movie. What is this? It's a cloud chamber. Okay, and it has alcohol vapor inside at minus 30 degrees Celsius, and you put uranium inside. What happens? It's actually radiating high energy particles, and you see those here. It's beautiful experiment. Okay, so something is coming out with crazy energy. Why did it stay there in the first place is a kind of a mystery. And so just to put everything together, what has happened until now? Until now, Maxwell came up with his theory of electromagnetic waves. Okay, then Planck said, no, wait, but it's made out of particles. Then Einstein said it has to. Then Bohr said not only photons, electrons also have this kind of quantized nature. Then Henry Becquerel, Marie Curie and other people said, but it seems like they are waves at the same time, they are particles, sometimes they are sitting inside the atom with less energy but still managing to get out sometime. Okay, so all of this seemed mysterious. So just to kind of enhance the beauty of this mystery, I'm going to do a couple of quick experiments. This is called a double slit experiment. If you do this experiment with normal balls, okay, you have balls. Okay, let me explain. What's the experiment? We have some screen and another wall with 2 slits. Very simple apparatus, and I'm throwing balls. Okay, and they hit the screen. Wherever they hit, I get the mark. As simple as that. Everyone agrees? Fairly simple experiment. You do this experiment, you will get something like this. You all agree? With classical particles. Now you do the same experiment, but let's say with water. What would you get? You get something slightly more complicated. You get what we call interference. Constructive, destructive interference. Okay, what does that mean? The water molecules are oscillating, and then you get the wave, and the second wave can come and they add up, the amplitudes add up, and you can actually get constructive and destructive. Sometimes they add up in such a way that you get no wave there. In some cases, you get even higher amplitude. That's what we are seeing here. So it's a usual experiment. You can go home and do this experiment. So these 2 slits are actually acting like 2 sources now of waves. Okay, this is the one source, and then these waves are interfering constructively, destructively. You get this. Okay, you do the same thing with electrons. Okay, let's look at a real experiment. This is what we get. What is happening? Initially, it looks like our usual balls hitting the screen. Eventually, see what is happening. We don't get 2 stripes. We get this interference pattern. How do you explain this? The only way to explain this is that these electrons actually, until the time we observe them, okay, I don't want to get into philosophical discussions about what it means. At the moment, the way to explain this is that these electrons are actually not these rigid particles, but extended objects, something like these waves. Okay, then you can explain all of this thing. What you can't explain is why do you then get this blip in a particular spot. Okay, for that you need to talk about something else which we call measurement. I'm not going to go into details, but this is basically we owe it to Schrodinger, but not only Schrodinger. As I have been telling you, one theme that I'm really trying to focus on is that the science is a team event. Okay, Nobel prizes are given to 3 people, 4, not even 4. 4 is not allowed. Okay, 3, maximum is 3. Okay, so but at the end of the day, it's actually, even Newton said, we stand on the shoulders of giants. Okay, so it depends on everything that has happened before. So you see, this is Solvay conference photograph. Almost all of these guys are Nobel laureates. Okay, only one woman scientist, Marie Curie. Okay, so I'm happy to see more women faces here. Okay, good. So in a way, we have progressed. Good. Anyway, so this, what Schrodinger did, again, he looked at all these experiments. He said the only way to explain it is, instead of using F equal to ma for rigid objects, what I'm going to do is I'm going to construct a theory that depends on waves. These waves, what is waving? If you ask me, it's a complicated question, so I'm going to avoid answering that question at the moment. There is some wave which I'm going to call psi, okay, for historical reasons. So psi, and then it has got some kinetic energy, it has got some potential energy, it has some total energy, and the total energy is conserved. Kinetic energy can get converted into potential, potential can get converted into kinetic. Like a ball that is rolling, let's say in a U-shaped whatever cylinder or something like that. You start with certain potential energy, it then gets converted into kinetic potential, right? It keeps oscillating, assuming that there is no friction. If there is friction, there is a dissipation, but that's another story. With this equation, again, no measurement, he could not, this cannot explain measurement. But then what we are saying is that electron is actually not like a point object, it's an extended object. If you do that, then you can actually get the interference pattern. Now the only difference is that the electron is not actually, in a way, if you read, you will get electron only at one spot. So the interference pattern is actually deciding the probability of where you find the electron. The interference pattern at the end decides where you find the electron. Okay, unlike in the water waves, you will actually see everything waving, but you don't ever see electrons simultaneously everywhere splitting. You see only at one spot. So that's the part that that we call measurement. He was able to explain. We have learned about this s orbitals, p orbitals. They're shaped, some are dumbbell shaped. What do I mean? What do we mean by that? That's basically, we are calculating the electron density cloud, like the simulations that we have done here. If you do the simulation, this electron is getting attracted to the proton, right? Hydrogen has a proton in nucleus, electron. So there is electrostatic attraction. So that generates a potential energy, that gives a potential energy. Now what did we learn from Planck? That there is this potential energy, okay, there is this bucket. Now if in the ordinary scenario, you can have water going to any place in that bucket, but then in case of hydrogen, only certain places you will have these electron clouds, and that's what this means. Okay, you can calculate all of these things. Okay, beautiful. So now we are understanding that all these subatomic or these particles, small tiny particles, they behave in a very different way than how we perceive the world. Okay, and that can be explained if we assume that they are not actually point particles, but they are extended objects. Okay, and then at the end, I'm going to say that this, in a way, automatically predicted quantum tunneling. You do not need to do anything. What I mean by that, consider a scenario that there is a particle here and there is a wall, okay, some barrier. Now, because the wave actually is an extended object, there is certain probability of the wave on the other side of the barrier. small, if you see, there is some certain probability, if when it hits, there is some probability here, right? Because it's an extended object, right? So what it means is that in those cases, although it does not have enough energy to jump over the barrier and go to the other side, there is certain probability that it may escape that barrier. Okay, because it's an extended object now. It's in a way, it's in a large area. The probability of finding that particle is not zero, even on the other side of the barrier. Actually, Schrodinger did not predict this. It was this person, George Gamow. Okay, George Gamow looked at, so this is where I'm going to explain radioactivity. All the other experiments we were managed to explain with whatever I have told you already. But radioactivity then in, I think it was around 1928, 29, around that time this happened. And Schrodinger equation that I showed was exactly 100 years ago, okay, 1925. Okay, so what George Gamow said is that you have a nucleus, and inside the nucleus there is this, I mean, the nucleus is made out of lots of protons and neutrons. Okay, they do have certain energy, but they are hold together because of the nuclear interactions. Okay, that acts like a barrier. It's holding them together. They have energy. They want to run away, but because of the nuclear interactions, they are staying inside. But they do have energy. What does quantum mechanics tell you? That there is a finite probability that someday they are going to escape. That's what's happening. In the radioactive substance, what is happening is that some of the nucleus is actually escaping, changing the nucleus itself. Okay, in the process, this nucleus is no longer, the element has changed, right? And that's how you explain. So this is how you explain tunneling. This is how you explain how the radioactivity is happening. So this, but okay, so this is my last slide on section 1. So now the crazy thing is this. We all understand that at this subatomic world or this atomic world, even few particles world, okay, we have to use quantum mechanics to explain all of these things. Okay, let's say we make peace with that. Okay, although we don't understand how, we say, okay, maybe we don't have enough brain power to really understand it, but mathematics tells you that it works. Now the issue is that at the end of the day, we are all made out of atoms. So if it's working at the scale of atoms, it should work at the scale of myself. So that's the kind of absurdity. So if you say that it works at the scale of single particle, what should happen when multiple particles? Why I don't see this person moving around, tunneling through the chair? What is happening actually? How can I calculate it? Okay, so this works at single particle, but the absurdity is that the world around us that we see doesn't work like that. Okay, so do we need different laws? Is there a regime where quantum laws are there? It's a different regime, classical laws are different regime. Is that the case? Or there is a link, and because of the bridge, I mean, certain things are happening, and eventually we end up with this classical world. Okay, and the progress has been very slow on this topic, but we did make a progress. So all of this happened in 1930s, and then it took certain amount of time to actually get devices that we can truly call macroscopic, and that's what gave Nobel Prize this year. Okay, so now in those devices they showed that this tunneling event is not happening at atomic scale, it's happening at billions of atom scale, millimeter, micron scales at least. Okay, and that's the next section that I'm going to talk about. Before that, I can take a break for 5 minutes, and then if you have any questions, uh, we can discuss. Any questions?
So, go ahead. Yes, actually, in my private practice, I have studied from the same school of it. So, what I remember. Hello? So in school, what we learned for this also.
Okay. In school, what we learned, I mean, the way you explained that, that alpha decay, loss of the helium particle via quantum
Right.
tunneling, yeah.
Yes.
So, but in school, what we have learned, like, nucleus holds together. Proton and neutron are together because of the nuclear force, and
Right.
that force operates when there is some minimum distance. Correct? Uh, and what happen in radioactive materials, like when a lot of nucleus size get bigger and bigger, so some proton or neutrons lose, there is an increase in distance, so nuclear force become inactive. That's how they lost it. Maybe it's a classical way of thinking.
No, you are on the right track.
Yeah.
It's not inactive. It's distance dependent, right?
Yeah, distance dependent.
Like if you go away from the sun,
yeah,
the gravitational force goes down.
yeah,
It's very similar. Okay, so the force that is holding them together goes lower and lower. So the outer kind of, if you want to think it like that, they are loosely bound.
yeah.
Okay.
If you increase the size of the
Yes,
nucleus.
yes, that is all okay. That is
Yeah.
all okay. Still, you can't explain the probabilistic nature of all of these events.
Yeah.
Why does alpha particle come out?
Why does alpha particle come out? And it's not like all the atoms are doing it simultaneously. It's not like that, right? Why should it be a probabilistic process where there is a small chance that it comes out? There is a finite chance that it comes out. Maybe you can say yes, yes, because it's unstable. But if it's unstable, then why not shade it out right away and become stable? That's not how it's happening. It has some probabilistic nature. Over the period of time, it's happening. And to explain that nature, you need quantum.
Okay. Thank you.
There anyone else wants to ask the questions? Or goes to the next part? Please feel free. Go ahead.
Yes, actually, I'm doubt, but I'm not sure whether it's
okay
or not. But so when you said about the tunneling, right? A particle that can move through tunneling to other side. But how much we are sure that whether it's a particle that moving other side of the tunnel or it's a property of tunnel that is moving? Like when you hit the tunnel, right?
Okay, so for that you need to do precise experiments. So here, these are at nuclear scale, right? The beauty of the experiments that we are going to look at is that they are done at a scale where you are creating the barrier yourself. You are making the barrier. This is made by the nucleus and all, right? The potential. Now the beauty, the reason why they got the Nobel Prize is because now they have actually brought this phenomenon on a scale where we can put together materials. So we have control over the barrier. We can apply voltage and change the barrier actually. So we have all the kind of control over it.
Okay.
Okay. And basically, once you have a control, then what you can do is you can do, let's say, voltage dependent experiment and show that it's changing according to the model that you're using. Right? You apply voltage, oh, the barrier is bigger now. Now the probability should go down. You can even calculate what should be the probability of tunneling. It matches.
Okay, here.
Thank you, sir.
This question, the heavier actinides,
Hmm.
their spontaneous decay either give up an alpha particle or an electron, the beta particle. Why not it have emission of lithium nuclei coming off or beryllium nuclei coming off? Why is it chosen to stick with the helium nuclei in its decay process?
I think it boils down to the probability and the energy. I mean, at the end, I think you'll have to really do the math and
It's actually due to partly nuclear forces. It's more stable to have together helium atom,
yes.
helium nucleus coming out.
There seems
That-
such a preference for helium.
Yeah,
Also,
because
it's not the
binding,
preference for
binding energy for the helium nucleus is more than hydrogen nucleus itself.
And
So
then
you'll find that it is.
you will see similar thing happening in Cooper pair, which is what I'm going to describe. Why do you get pairs? Only pair. You don't get more than two
Yeah.
because it's spin as well, right? That also makes it such a preferential state that you don't need to think about anything else, I think.
That's what I'm going to teach in the
No, but
class.
at least there I would say, but let's say if it got three,
Ah.
then it would be a fermion, and then you might have.
No, but you can have 4, right?
Yes, you can have four. Yeah.
Two, only two come.
Yeah, only 2 come, which is.
Boson.
Ah.
Is it? Okay, anyhow. Is there anything else?
Yeah.
Go ahead. Please. Hold both.
Able to finish at 12:30? Yes,
Yes.
no? Yes.
It may sound stupid, but can I ask
No,
how?
it's okay, it's okay.
I mean, how close are we to build a quantum computer that is practical?
I'll talk about it.
Later.
Okay, at the end.
Application.
At the end. Okay, I'm getting there slowly. We are still in 1930s. Okay, we need to catch up. 100 years to go. Okay, we'll get there. Yes.
Keep it close.
We are in the age of AI, robotics, and cloud computing. Do you think quantum will take over this? And when do you think it will?
Yes. So similar question. I'll talk about it at the end. Okay. Okay. So let's move forward. Okay.
One question.
Okay.
Okay,
Quick.
last
Yes.
question.
Sure.
Yes, sorry to delay the presentation.
No.
My question is, I didn't quite understand the meaning of electrons being an extended particle. Like, what does it mean?
Okay. So in extended objects, right? So we are not going to say it's a particle. We are going to say that it has got some wave-like nature to it. Okay. That's what I mean by extended object. Usually when we talk about electrons, classically, we think that they are point particles. They don't have any dimension. Usually but when you actually want to explain all of these phenomena, then you have to say that it's not true. What it is like an extended object. Okay. Okay. So this is actually very good because this is kind of a summary of part 1. What did we learn? That these are extended objects. Okay. And because of that, they being extended, they can tunnel. Okay. At a particle level.
Bonding also happens because of
Exactly. Because these electron clouds, they actually overlap. Okay, good. So now we are going to a very good question, because that's how I move to the next section. Okay, applying quantum to multiple interacting particles. Okay, so world around us, what do we see? We see all these metals, semiconductors, insulators, right? All of these things, right? I'm going to focus on electrical conductors, electrical insulators, right? But at the end of the day, you understand what I mean by electrical conductors, right? Copper, aluminum, right? So these are electrical insulators, right? So, but if you zoom in, at the end of the day, they have some constituent elements that are there, right? If you zoom in, actually with TEM, transmission electron microscope, you can actually get this kind of photograph where you can actually see waves. Okay, so in principle, you should be able to explain the properties of the material based on the structure of constituent elements. Okay, and the structure itself should be decided by quantum. You understand what I'm saying? So you start from the metal, you zoom in, you see all this structure happening. The structure is giving whatever properties. Like in case of polymers, you can extend them, elasticity, all of those things, right? You say that the properties that these materials have is because of the structure. But what is deciding the structure? The structure is getting decided by all these waves. How many electrons does it have? What is the extent of that wave? How can they overlap? Can they bond together? All of these things. Okay. So you can in principle calculate it. Okay. Now let's focus on metals. I'm going to focus on metals because eventually that is going to take us to the final phenomenon that we want to look at. So in metals, one way to look at it is that the outer shell electrons, they are loosely bound. Okay, so all of these red dots are actually the ions, the nucleus, okay, plus the closed electrons, and the outer electrons are in a way free to move around. and that's why they conduct electricity. When you add some voltage, these free electrons, they feel it, they start moving. Okay, that's how you explain a metal. Now you ask me, but they still feel resistance. Why would they feel resistance? Why do you feel resistance when you try to walk around? You bump into people, right? Collisions. That's why they feel resistance. They are colliding all the time with the ions, with themselves, right? They collide. Collide meaning this electron and electron. There is a cloud. Even if you consider a cloud, they will repel each other. Negatively charged clouds, they are going to repel each other. So that's what gives you resistance. Okay. So at room temperature, you have Ohm's law, V equal to IR. You apply voltage, you get current. What if, okay, so this is actually, I have kept it stationary, but in reality, this is what it is. Okay. So what happens is at room temperature, all these ions, they have certain energy, vibrational energy. So you see what is happening. We are at ambient temperature, let's say, at current temperature, they are all vibrating, jiggling around. We don't see it. Okay. That's why we say that the friction is a dissipative force. I'm giving my energy to the particles that are in the floor, they start jiggling. Kinetic energy. Okay. So if you actually have a very sensitive thermal imaging camera and if you place it near my feet, you will see that the temperature there increases slightly because I'm giving my energy to the floor. Okay. That's why when you slide, you lose some energy. You are giving that energy to the floor. So in a way, what is that energy? It's this vibrational motion. Okay. So as you raise the temperature, the vibrations are going to increase. What does that mean? Then the collisions are going to increase as well. If you all start randomly moving around, then you are going to, the probability of bumping into each other is a lot, right? So a question I'll ask, if I cool everything down, what will happen? What should happen? The resistance should go down, right? So that's what you see in this plot. For aluminum, if I plot conductivity as a function of temperature, you get something like this. The conductivity actually goes up. Okay. Now another question. When will it not have any resistance at all? If I show you this curve, when will it not have any resistance at all? Temperature, what temperature? Zero, absolute zero, right? Which is unattainable for practical purposes, right? Zero is impossible. Close to zero, yes, possible. Okay. So in a way, you cool everything down, something interesting should happen. Okay. So Anderson is kind of indirectly related to Philip Anderson, a great condensed matter physicist, I would say, is related to this story in a way, meaning he came up with this idea of emergent behavior, meaning I gave you the example of wetness or even the temperature. Temperature is actually the kinetic energy of molecules. We feel it as temperature. It's an emergent property. Wetness is an emergent property. So even if you know the underlying principle, that doesn't tell you automatically how the solid is going to behave unless you take into account all the interactions. Because of those interactions, something interesting might come up, a property that you did not envision for a particle. Like for H2O, there is no wetness. You put multiple H2Os together, you get wetness. It's a new property. Okay. So he came up with lots of these very nice ideas in 1950s. We are in 50s now. Okay. So here I have let's say aluminum. Okay. All these positively charged lattice points are basically ions, and I send one electron. See carefully what is happening. What is happening now? Not only that they are becoming still, the jiggling has gone down, but because of electrostatic forces now, this electron, when it tries to go around, it's trying to pull these ions close to itself. You understand? It should happen. It is happening even at room temperature, but they are moving so much that this effect is minuscule. You won't see it. You get my point? Okay. So this is with one electron. Let's add another electron. We have to jump to another Nobel laureate for that. Okay. So what is now happening is that, so there is this electron which is just moving. because it's moving, it's trying to drag all the ions with itself. Because of that, what has happened? The ions have come closer to each other, right? So the charge, positively charged distribution in that region has increased. You agree? Because the ions have come together. So there is a positive charge here, just behind the electron, right? So what does a positive charge do? It should attract another electron. So what's going to happen is that because these ions have come together, there is a positive charge that has happened here, and because of that, it feels as if these two electrons are now paired. They move together. They move together, and that's what we call Cooper pair. He got a Nobel Prize for this. Okay, so it's even more interesting because one electron is what we call a fermion. I don't again have time to go into these details, but it behaves like a matter particle. If you put together two fermions, they behave like photons, bosons. You might have heard Higgs boson, that got popular around 13-14 years ago. It was very popular. Boson, okay, is based on Satyendra Bose. Okay, that's the origin of boson, by the way, if you don't know that. He predicted it. Okay, so what is happening is, because of that, you can actually keep lots of photons in the same state. With electron, you cannot keep multiple electrons in the same state. But once you make this Cooper pair, what happens is suddenly this happens at a critical temperature. You agree? When the jiggling goes down by a certain amount, this pairing will happen, and it's not only that, it happens simultaneously throughout the material. So it's not a single Cooper pair that is floating around. Suddenly the whole material needs to be explained by a wave function. A whole material becomes a single object. You don't know where a single electron is. You don't know where a Cooper pair is. You have to actually, in order to explain this, you have to consider the wave function of a whole material. How big is this material? As big as you want, right? Obviously. So in theory, as big as you want. In reality, things get complicated. So this is now, what have we done? In the first section, we learned that quantum is applied to these small particles. Now, what have we done? We have stretched it, at least theoretically speaking, to a certain material which at low temperature behaves as if the whole material is quantum. So now we have an analog of a classical cat. Okay. Why cat? I did not discuss more about it. Schrodinger cat, I think I don't have time. That's the reason. But if you are interested, we can talk about it later. So yes, you can make it tiger. Okay. So anything that is extended object, right? It's not a single particle now. You have to understand that these are billions of electrons working together as one object. Okay, that's the only way to explain superconductivity. Okay, so now we have a cat. We still need to create a state which is what we call a cat state, which is a cat is a dead and alive simultaneously. Okay, this is something, a thought experiment that Schrodinger came up with, and there are lots of implications of this thought experiment, but one thing that we are sure about, that he did not like cats. Okay, his daughter actually confirmed that recently, that he indeed did not like cats. Anyway, the point is that we have a cat now, meaning an extended quantum object. Now what we need to do is, we have one quantum object which behaves like a live cat. We have another quantum object that behaves like dead cat. Okay, and we need to create another quantum state which is a combination of two simultaneously. Can you do that? Quantum says yes. How do we do that? These people did it, and that's why they got the Nobel Prize. Okay, so now we are in 1970s. Okay, so now what is the effect of all of these things? You don't need to actually go to zero temperature. Even at some finite temperature, you will see that the current flows without any resistance in these superconducting magnets or whatever, right? I mean, these objects, the current flows. Even if you remove the leads, the current will keep flowing. Then you will say, oh, it's a perpetual engine. It's not, because of several other reasons. If you have questions, then I'll talk about it later. Okay, so this is end of part 2. It's a small one. And then the final part, I'm going to discuss exactly what these guys did now. Okay, so I think we have now enough material to understand what these people have finally done. Okay, so before we jump to our Nobel laureates, one person I have to mention, Josephson. Oh, okay, so what he said is that this state I was talking about, dead cat, alive cat, simultaneously, he said we can do that if you bring two superconductors together separated by a thin insulator. If you do that, then what you are going to get is that this whole superconductor behaves like this wave, and there is a small portion that penetrates into the other region. This superconductor also has similar property. Okay, it also penetrates. So if you put these two together, then you will get a combination of those two. Okay, that's what I'm calling. This is, let's say, like a living cat. This is like a dead cat. Okay, just to keep the analogy going. Okay, so people actually, this is a fairly recent paper that I'm just showing how good we have gotten at making these materials. If you can't see it, actually it's like this. Okay, let me flip the. So this is exactly what Josephson said we should do. This is aluminum oxide, 2 nanometer layer of aluminum oxide. There is aluminum here, there is aluminum here. So you cool down aluminum to, let's say, tens of millikelvin, it will behave like this. How do you cool it? That's a different story. Okay, that's another Nobel Prize. But okay, so now what is happening? Cooper pairs can tunnel without resistance across insulating barrier because of quantum tunneling. Zero voltage current across tunnel barrier between two superconductors. So the current is, you don't need to apply anything. Okay, and the cat state could be realized. The cat state, by that I mean you can actually combine these two states and make a big state, which is a combination of those two. Okay, and finally we are in 1980s now. Okay, these two papers, 1985 and 88. So all these three guys are from the same lab. Okay, initially they did experiments in the same lab. So you see these two papers. One of them is a supervisor, one of them is a postdoc, one of them is a PhD student, and that's how they did the initial work. Obviously, when they went to their own positions later on, they had their own groups working on similar things. So in principle, what they have done now, you can create aluminum, you can deposit aluminum. You have superconductor, insulator superconductor. Then you can apply current through it and you can measure voltage. This now looks like a normal circuit. You all agree? Usual circuit. You can actually also have an equivalent circuit diagram. You don't even need to think about what is going inside once you create this equivalent circuit. Okay, but let's not worry about this equivalent circuit. This is what they actually were able to manage. Okay, and what did they show? Okay, this is most probably my like one of the last slides. This is exactly from their. I want to show something from the actual paper. Okay, this is the research article. Okay, I think you can understand this. What is happening here? That when they apply the voltage, the current, when they change the current, they are actually changing how the potential looks like. Okay, this is the potential, meaning I talked about hydrogen atom, right? It has some electrostatic potential. Because of that, you get discrete levels. That's what they are showing. If you have this kind of potential, you will get discrete levels predicted by Schrodinger equation. You can then change this potential. How? By sending in current, changing the current, changing voltage, lots of things. And then what they show is basically, if you create this kind of structure, then each level has some probability of tunneling depending on where that thing is sitting in terms of energy, right? If it has this much energy, then there is certain probability. If it's sitting somewhere here, then there is certain probability. So what they show in this plot is that The first thing is levels are discrete now in this potential. And again, this is potential of what? This is potential of this extended object. This is not potential of single hydrogen nucleus or anything. It's a potential associated with this extended Josephson junction. Okay, that's the potential associated with it. You calculate energy levels, they are discrete. So first of all, they are showing for this extended object, you get discrete levels. Second thing they showed is that because the potential drops like this, although if you are in this level, there is not sufficient energy to actually cross, but it still does. They actually calculated tunneling probability as a function of this barrier height, and it matches exactly with what the predictions are. Okay, so last two slides. So you ask me, so what, right? I mean, so what? Macroscopic tunneling, so what? Okay, I'll give you one answer that many people like, and I will end with the answer that I like. Okay, so one answer is because we can create new devices with it. Okay, what is this device? You use a similar structure. Here now you have two junctions. So you have a superconductor, and two insulators. If you use this, then what happens? Remember this video when the superconductor was floating on the magnet? So it tends to repel this magnetic field. So it's very sensitive. So in a way, you can actually measure magnetic fields of the order of femtotesla, femto meaning 10 to the minus 15 Tesla. Just to give you some idea, Earth's magnetic field is microtesla. 50 microtesla is Earth's magnetic field. Okay, micro is 10 to the minus 6. Femto is 10 to the minus 15. Okay, now you ask me, why do we care about 10 to the minus 15 Tesla field? Whenever you do any precise measurement, you understand something new about that system. Whenever you understand something new, so you can actually use this. People are using this to understand how our brain works. Why? Because neurons are actually sending signals, electric signals, right? Whenever you have electric signal, it will generate magnetic field. These are very tiny magnetic fields. But you put these squids on your head, you can measure these magnetic fields. You can actually track how neurons are talking to each other. Okay, that can allow you to understand how these different disorders occur in the brain. Okay, that's one. This is another hot topic, very hot, too hot for me at the moment. But anyway, so it's the same technique. I already told you that with this technique you can get discrete levels. But because this is now happening at micron scale, millimeter scale, this is something that we can control quite easily. Okay, it took 50-60 years. Okay, but anyway, meaning what I'm trying to say is that now I don't have the whole kind of way to explain why quantum computers are better than classical computers. As far as certain problems are concerned, you always need to understand that quantum computers are better for only certain problems. Why they're better? In a nutshell, because a classical computer uses a bit which is either 0 or 1. Quantum computer uses a qubit, two-level system, or two-level, let's say this level and this level. Okay, but you can be in a superposition state. 0 meaning this level and that level simultaneously. So you can probe, it's like ultimate parallelization. That's answer number one. The second important answer is entanglement and other things. I'm not going to get into that. But this is kind of in a nutshell why quantum computers can solve some problems, optimization related problems in many cases, much faster. In a way, they are parallelizing everything. Okay, if you ask me, I want to go from here to, let's say, Besant Nagar beach. Okay, what street should I choose? Okay, how would a computer solve this problem? It will calculate how much time it takes, all the paths, not simultaneously, differently. Then it will say, oh, this path is the best path. Okay, the quantum computer is supposed to do that, to solve that problem in a very different way. It will try all the paths simultaneously. and it will give you the answer. Okay, that's why in principle it can perform much better. Okay, so you can use this structure as a building block of a quantum computer, and that's what many companies are doing at the moment. This is a new chip that Google has. They call it Velo. Okay, a paper in Nature came out like 3 days ago. They have done something quantum supremacy, and here is a local guy standing next to. I say, look, you know this person, Sundar Pichai, right? You know where he did his high school? Here, Vanwani. Okay, here. So he's a local guy, Chennai. Okay, so now he's standing next to this dilution fridge. This dilution fridge allows you to go to tens of millikelvins that you. So there are these, so you cool it down, it gets complicated, but whatever it is. And now they are trying to actually build these things, put multiple of these together, let them interact and use them to do some computation. Okay, so this is the answer that people like. This is my answer. Okay, this is my answer. This is why I care about Nobel Prizes. The true reason to celebrate the Nobel Prizes lies not only in their practical outcomes, but in how they remind us of humanity's greatest strength, our unending curiosity and our desire to understand the universe we live in. Okay, that's why I like Nobel Prizes. That's why I like to interact with you. Okay, thank you.
Thank you for your excellent talk. Now we are in the situation of going to question answer sessions. And before we start the question answer session, library would would like to give a small memento.
Thank you so much.
Okay, now now we are starting okay, yes. Please, those of you who want to ask, who want to ask, please.
You went from this to time travel.
But it's not part of the yes.
Depends on how you define it. You seen Interstellar, the movie? That kind of time travel is possible.
It can be made in any movie.
Meaning, in principle, also you go close to an object with very high gravitational field. You see, let me tell you a different story. Okay, the reason why I like to really emphasize this part is because if someone asks a question to Einstein saying, "What's the point of your general theory of relativity? What instrument can you build?" He would have gone mad. Okay, but now you won't actually be able to move around without general theory of relativity. You know why? GPS. It uses general theory of relativity. Why? Because the satellite is not very close to the Earth's surface. We are closer to the Earth's surface. So there is a time dilation happening. So it is. Time travel is already happening. Okay.
Okay, go ahead, please.
Yeah.
That is for the YouTube.
Okay. So, like, forgive me if my question is
No worries.
basic. So, I have two questions. The first thing is, you said that if in case of Google Maps, if it optimizes which route is the best thing by separately evaluating each route when it comes to classical computers, and quantum computers parallelly do the same thing, concurrently or something like that. So, like, what if there is a mechanism where 3 classical computers are used simultaneously to evaluate each route at the same time? Will it be considered as a quantum computer? Is my first question. So my second question is, I could see that a lot of people are developing quantum computers in a different way, something like a silicon based, or like when it comes to Intel and Microsoft is doing something else. And they're also predicting that quantum computers in few years will be able to break Bitcoin type encryptions, and due to which blockchain will be obsolete or something like that. So if that's the case for the Bitcoin encryption, what will be the case for banks and other institutions? And which type of quantum computers do you think that will break this type of encryptions first? Because there are a lot of types of quantum computers.
If I knew this, then I would have been like a billionaire, okay, at the moment.
Okay.
Okay. I'll give both the answers. The first one. So what you have to do is you have to calculate how many bits you need to solve a particular problem. Obviously, you can chain multiple CPUs together and do parallelization. What you have to do is you can actually, based on the complexity of problem, you can calculate how many classical bits you need to use to solve that problem versus how many quantum bits you need to solve a particular problem. In case of quantum, it wins if you have hundreds or thousands of qubits, then the kind of computation that these qubits can do actually surpasses trillions and trillions of bits, classical bits. Okay, that's answer to the first question. The second question is, obviously, quantum computer depends on how well you can control this two-level system, these two discrete levels. At the end of the day, what you need is a two-level system and then multiple two-level systems that can interact with each other. Meaning, you want to generate, like in this case, they are generating using Josephson junction, this superconductor, insulator, superconductor. That's how they are generating these levels. You can generate these levels by using something known as quantum dots. You can do that. You can do it using some defects. There are several possible ways of doing it. Now, which one of those technologies is going to win? Only time will tell. Will it win at all? Even that is not clear, if you ask me. Okay. Yes.
What's your favorite technology, sir? Like you have some.
Oh, no. That answer I can't. Go ahead.
Sir, good morning, sir.
Yes.
You showed that the electron will pass through that slit by extended property.
Yes.
You showed that. Can we say confirmation about the electron, whether it is a particle or a wave bundle?
Okay. So I sometimes give these public lectures on only Schrodinger's cat. Okay. Maybe if I'm giving that lecture, I'll let you know, because people can come up with ingenious experiments to understand all of these things, and things get more and more complicated. So yes, you can put some cameras to understand where the particle has actually gone through. You can do that, but when you know that, there is no interference. Okay, so things get complicated.
Yeah. Thank you, sir. Thank you.
Yes. Okay.
So in the first place, thank you so much for this interactive session. I truly enjoyed it, and for taking us back. So my question is, will inertia be a probable inhibiting factor in quantum tunneling? Or did they even discuss about it? Or is it a stupid thing to be?
Okay, so I'll try to give an answer to this. It's not a stupid thing. There is a Nobel laureate who thinks that this is the solution to the problem of decoherence, which means the thing is this. When you say inertia, you're thinking of mass in a way, right? Yes. So the point is, if you look at the strength of gravitational attraction versus the strength of all of these other forces that we are considering, even electrostatics, nuclear forces, if you consider, then they are far greater. So how it's like 30 orders of magnitude difference, 30 orders of. So in a way, in all these particle experiments, we don't even need to consider masses. Now there are effective masses that come into play when you are discussing solids, but that's a completely different phenomenon. So you do have to consider masses in principle, but not the way, meaning gravity is not a problem.
So it gets nullified, is it?
Not nullified, but okay. So yeah, it complicates, meaning you don't need to consider mass interaction. You are not considering that interaction is not part of the Schrodinger picture. You don't need to. You can, but the effect is going to be minimal because it's 30 orders of magnitude.
Thank you, sir.
Okay. Go ahead.
Thank you. So
we have now seen that we can make a larger object act like a quantum object
Yes.
and make it phase through. So would there be a time where we could create constructs which can be controlled, whether it can allow us to phase through or objects to phase through? Like, could it be possible in the future with
Okay.
better technology?
I can't predict. That's the real answer. But let me tell you something, which is kind of very philosophical question. If you pass through that wall, I'm not even sure that the person that goes through the wall is the same person. How do you know that? Right? So this is a philosophical thing. Anyway.
Okay.
Thank you, sir.
Okay.
Well, I mean, we discovered quantum tunneling. Can this be used to explain how in astrophysics this be explained, quantum tunneling?
Yeah, I mean, there are lots of nuclear processes where you have to use quantum tunneling.
Neutron star.
Yeah, exactly.
Certainly, energy creation is actually.
Yes.
I have to ask in the terms of neurons. Actually, I'm a psychology student. You explained about that mood disorders, right?
Okay. Yes.
Yeah. The squid will help to determine whether, but brain will excrete three types of waves:
Okay.
alpha, beta, and theta. Theta, which refers to calmness, deep relaxation, and alpha is very relaxed. Only beta is for anxiety level. Whether the theta waves will be nullified by this.
Okay. So it has nothing to do with alpha, beta, theta here. The point is that every wave that a neuron sends to another neuron is an electrical signal. You agree with that?
Yes, sir.
Right. So every time there is a current, you will get it will generate a magnetic field, and that's what we are detecting. So at the end, what you are trying to see is that how these networks of neurons are getting changed over the period of time. Or people are doing actually these brain organoids related experiments.
Yeah.
I don't know if you know about organoids. You can start from stem cells and grow a brain in petri dish. So what people are trying to do is people are trying to detect the onset of different disorders, how they connect. And for doing that, you need to know local information, how the signals are getting sent. And for that, you need these kinds of very precise instruments.
Okay, so thank you.
Yes. Okay.
Oh, hi, sir. Regarding double slit, regarding double slit experiment, we always do double slit experiment in the room temperature, right? Room temperature and energy in the atmosphere of room temperature. Energy can't be same for all points, right? All each and every point energy can't be same for each and every point.
Yes.
Right. At the same time, the results of the probabilities of individual double slits experiment, trial 1, trial 2, probabilities also results also can't be same, right?
You can take all of that into account.
Yeah.
And you will still get the same thing.
Averaging.
So
averaging, you have to do averaging.
Yeah. So is this? I mean, the wave, the double. I mean, double way of what to say?
Yeah, it's a duality. Wave and particle is.
It's a duality, right? Is that because of the changes in the energies between in between the, I mean, the slit and the emission of light?
Okay, so you are getting somewhere, maybe you are talking about what we call decoherence, the interaction with the environment.
Yeah.
Some of it can explain this thing, but not entire thing. Okay. If you want, we can discuss later, but yeah.
Definitely.
Thanks. Okay. Are there any other questions? Okay, last question.
Yeah, I have a question. I mean, it's
Oh, you have to keep the mic close to your mouth.
It's regarding the opportunities in quantum in India. Like,
Okay.
how far the research is happening in India? Like, in how actively the IITs and IICs are
Okay. Yeah, good
participating.
question. Good question. So,
Sociological.
good question. So, India is a complex thing that you already know. So, I'm not going to get into all the politics and all. Scientifically speaking, we are working on quantum technology. Actually, in TI for Bombay, we already have a quantum computer. Okay, 6-qubit quantum computer based on the same technology. We already have it. Yes, Vijay Raghavan. Okay, so he's going to visit IIT Madras. So we collaborate with him, and so things are happening. There are squid-based technologies. There are other technologies that are coming up, but it's still a futuristic field. Meaning, if you ask me what are the job opportunities, I wouldn't say that there are any at the moment. Not in the near future. So I tell my PhD students that you need to know other skills so that you can get the job. No, quantum is not sufficient. Thank you, Steve.
One follow-up. So, I think that, India is yet to even make a 25-qubit quantum computers,
Yes.
whereas a lot of other countries. So, it said that India is yet to make even a 25-qubit quantum computers, whereas other countries are marching towards surpassing 125 qubits and stuff like that. So, does it mean that India lags, or is it equivalent to RAM in a classical computer? And will it be the first country which solves the proper quantum computing technology will win the race, or who solves the most qubits will win the race?
Well, that's a very futuristic question. I'm going to not answer any of that, and I'm just going to say that as a society, we need to be more curious. We need to actually ask questions, and we need to inculcate this attitude of exploration, which is kind of really missing in our society, right? So that's the only way to solve these bigger problems. Everything is linked together. Unless you remove the rigidity out of your brain and think about the whole, all of these problems in a wholesome way, it's not going to. Okay, so that's my philosophical answer to your question.
I don't care whether China finds it or somebody else finds it. As long as it's found, it's fine.
Yeah.
Okay. Aditya, can you go on that? Please. Yeah.
So, you had a feeling of seeing a movie. There was a break also. I hope enough curiosity is generated in your brains. So thank you for generating so much curiosity in the audience. And this will be available in YouTube also. You can repeatedly see this any number of times. It will be available. All the 95 previous lectures also available. Okay. And thank you all for coming in large numbers. And those who want the participation certificate, submit the feedback. The QR code is available on the desk. Please scan it and submit your feedback. You'll be getting a participation certificate. And one announcement, next week, we are having a similar lecture from a professor from IIT on chemistry Nobel Prize, that is metal organic framework. Okay, please do attend and spread this message. Thank you all once again, and thank you the library authorities, Anna Centennial Library, for arranging this excellent location. I think we will not get a better location surrounded by all books, and specifically today, this books on quantum mechanics also is kept here for your, generate the curiosity.
Yeah, just one time. How many of you are from colleges or college students? Quite a lot. I'm very happy to see this.